Okay, today I'm going to talk about momentum and impulse. This is part one of a two-part series. The other part is on momentum and collisions. This is more of an introduction. This is Unit 5, if you're keeping track of that anymore. Momentum is related to Newton's first law. It's mass in motion. It's actually a numerical measurement of the inertia of a moving object. We never talk about momentum in an object that's at rest. We only talk about moving objects. It is simply the product of the mass of the object times its velocity. Since velocity is a vector, that is going to make momentum a vector quantity. Most often we use pluses and minuses, especially in collisions. And we'll find out later when we start talking about collisions, momentum is conserved. There is a law of conservation of momentum, very similar to the law of conservation of energy. And momentum is also conserved in action-reaction, Newton's third law situations. The formula for momentum, there are a couple of ways it may take. P equals mv. M is already mass, so they use P for momentum. I'm not sure why P, but it doesn't really matter. These formulas are on your reference sheet. So P is equal to the mass in kilograms times the velocity in meters per second. The other part of the formula, delta P, or change in momentum, is equal to momentum change in velocity. It's the same kind of thing. These units, and again, since this is a vector and sign matters, change in velocity is going to always be expressed as final minus initial velocity. The units for this thing are times a meter per second. This is not a Newton. It's missing another second. Divided by another second. Newton is kilograms times meters per second squared. So it's a little different unit. There is no derived unit for momentum. We just got to use the kilogram times meters per second. If you have a moving object, it has momentum. And to stop a moving object, we have to apply a force against its motion. So the force vector is going to be in the opposite direction of the motion vector. And that force is going to be applied for a given amount of time. So the more momentum an object has, the harder it's going to be to stop it. You can think of it as be a whole lot harder to stop a loaded tractor trailer than it is going to be to stop something like a Honda Civic. So it's going to be a big difference. So either momentum from a heavier object or momentum from a faster velocity. So if you have a large amount of momentum, it's going to take a greater amount of force or a longer amount of time, or it could actually be a combination of both of them to make that object stop. In collisions, we also run into something called impulse. The impulse is the force that changes the momentum, but it is a force that is applied for a specific amount of time. That's the impulse, and we're actually going to refer to that as force applied over time, F delta T. The result of the force is going to be that the object can slow down or it can speed up. We can change momentum. We think a lot of times of momentum of stop an object, but it also takes an impulse to make an object change direction or to make an object speed up. Like if you're hitting a baseball with a bat, there's an impulse the bat applies to the baseball at the time of contact. And the nice thing about it, we can set impulse equal to change in momentum. So that lets us do some interesting things with formulas. But first, the formula for impulse. Impulse is this one's also on your reference sheet, is given as J. And it is equal to that force delta, F delta T, a force applied for a period of time. The units on impulse are identical to the units on momentum. So you can probably see where this is going. We can set change in momentum equal, and that's why I gave you the change in momentum formula. We can set change in momentum equal to impulse. So let's do a problem where we have to do that kind of. We have a 2,200 kilogram SUV, and it's traveling 26 meters per second. And basically there are three ways we're going to stop this SUV. We're going to stop like a normal stop, gentle application of the brakes, and it'll take 21 seconds to stop it. Or we can see something just running the road in front of us. We slammed the brakes, the brakes kicked in, everything worked, and we stopped it in 5.5 seconds. Or we didn't, and we stopped it in 0.22 seconds with a tree. And what we're going to do is we're going to figure out the force exerted on the SUV by each of these stops. So the first thing we need to do to solve this is we have to calculate the momentum. So the momentum P is equal to mv. We said the mass was 2,200 kilograms, and it was moving at 26 meters per second. So that gives us a momentum of 57,200 kilograms times meters per second. And I'm not going to round to sig figs yet, because I'm going to use this number in three more calculations for each of the three scenarios. So the numbers to remember here is 57,200 kilograms times meters per second. So step 2, we're going to look at each scenario, and what we're going to have to do is set momentum equal to impulse, or the change in momentum equal to impulse. So P can now equal, instead of mv, P is now able to equal F delta T, which is the formula for P equals J, so it equals F delta T. And we're going to have to rearrange. I want to solve that formula for force. So force is going to be equal to the change in momentum, and we're going to make that just change in momentum since we did stop a vehicle, over delta T. So 57,200 kilograms times meters per second divided by 22 seconds. And that is going to give us 2,700. And I guess our units are kilograms times meters per second. We divide it by seconds, so kilograms times meters per second squared. Hey, and this is a force, so that makes sense. We're in newtons. So if we gently brake, we'll have a takes a force of 2,700 newtons applied over 21 seconds. All right, let's look at the second scenario, and I'm not going to rewrite the formula. So F is going to be equal to delta P over delta T. 57,200 kilograms times meters per second divided by, this time, 5.5 seconds. So our force here is going to be 10,400 newtons. Greater force, but it's only applied over 5.5 seconds to cause the same change in momentum. I think you can see where this is going with the tree, but we'll calculate it anyway. So again, F is equal to delta P over delta T. Delta P, again, the momentum is the same no matter how we stop it, times meters per second, divided by 0.22 seconds, and that is 260,000 newtons that's applied over that short 0.22 seconds. A lot more force, but it's only applied over time, and that's why you would see catastrophic effects to the vehicle, and unfortunately occupants too, probably, in this situation. One last little thing to wrap up this first half of the notes, with action-reaction situations. In an action-reaction situation, momentum is conserved And this is something like this cannon recoil. We fire a projectile. We have this relatively small cannonball that has a relatively high velocity going out. And then the cannon recoils in the opposite direction, according to Newton's third law. It has a lot larger mass, so its recoil velocity is going to be smaller. But when we can, because momentum is conserved, the momentum of the ball and the momentum of the cannon recoiling are going to be equal. So M1V1, which we're going to say is the mass and velocity of the cannon, is going to equal the product of the mass of the cannonball times the velocity of the cannonball. So pretty much we know the momentum. We just set this equal, and we can of course solve this for M1, V1, M2, V2. We can solve for any of these things. Okay, that's the end of this part of the notes. The next video is going to talk about a little bit more about momentum and impulse in collisions, and a little bit more on problem solving with this.